Okay, so let me talk to you about the colligative properties, and this is a property that do not depending on the chemical species type, but only depends on the number of moles or numbers, absolute that you put it in. And this colligative property itself is, you just need to know the language itself. Sometimes they just ask you that, what do you mean by this colligative properties? And then let me write it here. This one only depends on the number of solute. Oh, I guess we're still using the symbol B, right? And so which means essentially solute particle, right? Sometimes the people call it number of solute particles, solute number of moles, right? And well, it just says number of molecules. So it's just the number matters, but the more important one is not on the chemical identity of solute. This is what makes a big difference. Okay. Not the identity, the chemical identity of the solute. I guess it matters a little bit though. This solute, by definition, it has to be dissolved in the solvent. Okay, if it's not dissolved in a solvent, the whole thing doesn't make sense. So think about it. If you put a sodium chloride, calcium dichloride in water, they associate into sodium plus, chlorine minus, calcium 2 plus, 2Cl minus, right? So effectiveness is 2 times molar. This is 3 times molar. So by putting the 1 moles of this, you are generating the 3 moles of ionic species. So this one itself will be a much more effective in terms of counting the numbers to change and for us to see the colligative properties. So this is the one. I mean, think about sugar. Sugar is a molecule, right? You can put the sugar into the boiling water to cook the pasta at higher temperatures, right? Do you want to put small dash of salt or a big spoon of sugar to get the same boiling point elevation? Because what I'm is, I guess the sugar molecule is 1 mole is 1 mole. So in the molecular way, molar mass is a lot bigger. So the 1 mole worth of mass is a lot bigger here compared to the other one, right? So it is just when you see the numbers, and that's what it means. And what are the examples of colligative properties? So this is their definition. And the example. Boiling point elevation. Freezing point or melting point depression, and then what we call the osmotic pressure. Okay, this is what we call using the symbol pi, and these are the examples. And there are more, but these are the most famous ones. And we are using this to cook pasta, to melt the ice, right, in the winters. And this one is actually we are using for measuring some molecular weight of polymer compound that or some kind of macromolecule. In old days, people used to do that. Okay? When you don't have some fancy tools like mass spectrometry, this is actually the one that was very popular. I guess not anymore. Okay, so but now this is probably a topic that you heard it before. Why this is all coming from? This colligative property is essentially, it has something to do with chemical potential of solvent in solution. So this one is being chemical potential of A. You know what star means? Star means pure solvent, right? Chemical potential, pure solvent plus RT natural log XA. So that's an equation that we just learned last class. And I tell you before, chemical potential solution is lower than chemical potential of liquid. For liquid in solution, they have a lower chemical potential. So you're lowering the chemical potential. So the water, when you put the sodium chloride in your cooking pot, water chemical potential of liquid is coming down. They became happy. So they became happy. They expanded the region of liquid existence. So boiling point will be higher, freezing point will be lower because of that. And the contribution is coming from here. Right? And if you look at that, how much of the reduction, this is a reduction. Of chemical potential, right? As a liquid, and you are lowering this. And this one is essentially mainly governed by natural log of XA, and the XA is a mole fraction, right? Has nothing to do with the chemical identity of something that we know, right? So therefore, it is actually one of the very simple way to explain that is a colligative problem. Okay, so that's the one. Okay, so I explained that last time. When your temperature and looking at the chemical potential of different phases, solid has a lowest slope minus delta S for the solid, and the gas is the steepest slope for the chemical potential as a function of temperature. So this is a solid, this is a gas, and then I told you that that's a liquid has an intermediate slope. So remember what? I'll write it one more time. So this equation for given pressure is minus Sm, right? So that's the one. So the slope is negative, but there's a different degree, and this is for the liquid. And then when you have something like a solution, your chemical potential is going down like this, lowering that, and this reduction amount is essentially RT natural log XA. And this is what this equation is telling you, how much of the reduction you have. And so therefore, this is a melting point, that's a new melting point. You widen, essentially you widen the existence for the liquid phases. And this used to be a boiling point, now that's a new boiling point. So this is a boiling point elevation, melting point depression, and so you used to have this small narrow window from the pure. This is a pure liquid, and this is a solution, and then you have widened the liquid region because they are. I like to use this one, right? So as a solution, they are happy. So this is a happier than when you used to be as a pure one, right? So you're happy. So that's the whole idea. And then people start to want to use this concept actually to have a predictive knowledges. And then from the fundamental understanding, this changing this one is related to mole fraction of your solvent. And the human nature is, I don't want to describe the concentration of my solution in terms of mole fraction of solvent. Doesn't make sense. Okay? So I have a water, if you put a salt, and then you want to concentrate, you want to describe your concentration in terms of solute concentration, not in terms of XA. So they actually derived an equation, and I'm going to actually jump ahead and trying to explain. show you the equations. It's a lot of derivation, but I think that I just do not want to spend more time in derivation. So I'm just going to show it to you. The boiling point elevation is KB, which is a number, and then this is a P, which is a concentration in terms of molarity. Okay? So people has tabulated this value, which is a boiling point elevation constant, in terms of concentration and molarity. You know what's the molarity unit? Mole of solute divided by kilogram of solvent, right? This is actually a very lazy way for you to do. So all you gotta do is actually you separately have a kilograms of solvent. I guess how many grams of salt solute? You put them together and you just mix it in. So you don't have, we are dealing with the overall solid solution volume, and this is much easier for people to think about it. So that's the one, and I guess the same thing. Tm is Km times B. So it's just matter for you to choose what concentration unit, and in the community that people trying to make the colligative property in use, and they want to tabulate those numbers, and they are using the concentration in terms of molarity. Okay, so I guess this one has a unit of degree C divided by mole per kilogram, right? Or you can say, well, I don't Kelvin. So that's a funny unit. So it has a very funny unit of mole per kilogram. So therefore, it is a Kelvin mole times kilogram. It has a very strange unit, but that's the unit that they use. But what I want to say, instead of trying to spend the time in derivation, this is the one depends only solvent. Okay, so you can make a guess, right? The chemical potential is related to Gibbs free energy, and the boiling is liquid to the gas, so this must be delta H enthalpy, right? Delta H vaporization. Heat of vaporization is the one for the solvent, not the types of solute that you put it in. Same here, in the heat of melting, heat of fusion is the one that related to. But what matters is, given that if somebody gives what is your solvent and what types of, what type is not important, what's the molarity of your solute, and I can give a prediction of the value of boiling point elevations, freezing point depression. And I want to actually give you the numbers. So the KF, the freezing point, is 1.86 K kilogram per mole. Okay, so that's for water as a solvent. Okay, and KB, boiling point elevation, is 0.51 kilogram. So now somebody gives you how much of the salt that you put it in, you can convert the number of the mass into the number of moles, and you see what is the volume of your water in a cooking pot. You can calculate the molarity, and the molarity and multiply by this number will be how, what is your boiling point elevation. And you put a 2 spoonful of salt into the cooking pot and so on. So that's, this is a number that is tabulated in the textbooks. And textbook 5B1. Okay. And you can find it for other solvent as well.